historical development term. So we have figured out Klein-Gordon equation, and we have seen there are problems. Okay, so we discarded this equation for the time being. Discarded as a wave equation, yes, as a single particle. Okay. So we have seen we cannot take it as a single particle wave equation. Now let's go to the next. It was actually Dirac. Okay. Okay. So Dirac attempted to figure out a kind of wave equation for spin half particles. Clear? So when you have seen there are certain problems with phase equation like negative energy solution, probability density interpretation, and so on. So these kind of problems were there as a single particle equation. Now Dirac attempted to write a wave equation for an electron. Let's say electron carries spin half. Okay, so Dirac was attempting to formulate a theory for an electron. Clear? Okay, so what Dirac proposed, the idea goes like this. So you are having this is as an energy relation. Okay. So let's take E is equal to P square C square plus M square C raised to 4 root. So this is the energy momentum relation. Clear? So and if I have a wave equation, Dirac proposed a wave equation like this, partial by partial d psi, okay, as a linear as a first time derivative of psi, okay, and like this thing h psi. Okay, so this is just a proposal, huh? So you know this way kind of equation, you know what you need to know. You need to know h. Clear? So what was the Klein-Gordon equation? What is the Klein-Gordon equation? You are having double time derivatives and double space derivatives. Clear? Okay. So now instead of having, we have seen if I require a double time derivative, if you have a double time derivative in your equation, you require to know what is the wave function and its first time derivative to evaluate its, the dynamics. Clear? Clear or not? Okay, so instead of doing that, if you throw away that kind of concept, you start with the first time derivative. Okay? You say, let's say you are having a first time derivative in psi, some wave function, okay, and assume this h to be of the first order in space derivative. Clear? So this was the idea of the Dirac. In a sense, let's say if I will give a quadratic equation, some quadratic equation, bx plus c, and I want you to factorize it. Okay, so if I take, let's say, the root of this quadratic equation, okay, it is a symbolic thing, eh? So what it should be, when you take the root, it means it should turn out to be the linear function. Clear? So let's say its root is something, let's write bx plus e. Clear? So you can square the both sides, and then you can figure out this g in terms of a and e in terms of all these coefficients. Clear? And you can say the square of this object is like this. Clear? Okay, similarly, if I take the root of this thing, okay, Dirac assumed this h, okay, so what is the h corresponding to this thing? Tell me. So last time we have seen the h corresponding to this thing is like c square h dot square nebula square plus m square c raised to 4. Okay? Clear? Or in other words, you can have simply like this thing, c square, the momentum square, plus c square. This is an operator square. Clear? You cannot take the square root of an operator. It is mostly undefined quantity. Often it is an undefined quantity, square root. Okay, but you assume if I take the square root of this quadratic equation, okay, what it should yield me? Linear. What it should yield me? A linear equation in terms of p and this this object, sorry, it should be linear in P because P is a variable there. Okay, you fix this quantity, this is a variable quantity. Clear? This way, like you are having x square, so it turns out to be linear. Clear? So this is an attempt of the Dirac. Dirac proposed this kind of equation. Okay, like so it is just the proposal for the time being. Then we will interpret these kind of equations. Okay, a linear. So he started with this kind of equation, alpha dot p plus some beta m c square. Clear? Okay, you got my point. So what this is this linear in P? For the time it is ad hoc in nature. So while it comes from, okay, so you can think this simply as a postulate for the time being. So you are having first derivative in time and first derivative in space. Clear? Got it? So this is the assumption of the Dirac. He proposed this kind of equation for an electron. Okay? Now the point is, what are unknown quantities here? Alpha and beta. Okay? So for this equation to be relatively invariant, okay, that means invariant under Lorentz transformations, these alpha and betas are not some simple numbers. They turn out to be matrices. Clear? We'll see in detail. Exactly. First, you should have to feel this equation as a linear in P. Clear? So look at the difference between Klein-Gordon equation and what? Now this equation. Clear? So this contains first time derivative and first space derivative. Clear? And in Klein-Gordon equation you are having double time derivative and double space derivative. Clear? Okay? So now let's write it in the extended version. Okay, so it is C. Let's write some alpha 1 partial by partial x1 plus. So what is P? Tell me. So let me write first. What is P? Minus I cross this number. Okay? So I should not put it. It is an operator, sorry. It's an operator. Clear? So P is an operator, right? It contains, what is this P? So it is an operator for Px component, Py component and Pz. Clear? Okay. So now let's write it. So and psi is simply a wave function. Let's consider this as a wave function for a spin half particle or an electron. Okay, some particle. Once we take the non-relative limit of this very equation, you will see it reduces to a wave equation for a particle carrying spin half. Okay, that we call as a Pauli equation. Okay, so we'll see in a moment. No issues. Okay, so now let's write it. So you are having minus stress. Okay, C. Then so now let's write it. What it will be? So it is alpha 1 partial by partial x1 plus alpha 2 partial by partial x3 alpha, sorry. Okay? So this all is acting on psi plus beta mc square psi. Okay? Got it? Okay. So now you can rewrite it. Okay, so what is the nature of psi? So this is your Dirac equation. Okay, the first assumption Dirac made. So this psi is not a simple single component wave function. Okay, so it is some kind of vector. Let's write it as it is having n components. Okay, clear? because I'm saying for this equation to be invariant under relativistic, okay, invariant under Lorentz transformations, these alphas and betas, okay, the alphas and the beta, they are not the numbers, they turn out to be matrices. So that means we can interpret this equation as a matrix equation. Clear? So if, let's say, if this is a matrix, this is a matrix, this is a matrix, this is a matrix. Now psi must be a column vector, okay? You got my point? Because you are having a psi here, so what it will be? Let's assume psi to be a column vector. Clear? So you are having a column vector on left hand side, and you should be having a column vector on right hand side. Okay? So that means this object, these alphas, alpha 1, alpha 2, alpha 3, and beta, they must be matrices, square matrices at least. Okay? Clear? So that matrix multiplication is valid, and you will get a column vector on the right hand side as well. Okay? So let's assume this psi to be an n component vector. Okay? It is having n components. Okay? So let's write then this very equation. Okay? So let's write it in the component form. So therefore I can write for n, let's write some sigma to component. Okay? Sigma is going from 1 to n. For any component, let's put it in the matrix multiplication form. So it is minus I h cross c. Okay, so can you tell me how to put? Let's write summation over I, alpha I, partial by partial xi. Okay? So this is a matrix. Is this a matrix? Okay, so let me write it this way. Plus beta mc square. Okay, so this object is a matrix. Let me write, anybody? Sigma tau. Let's write psi tau. Okay, so simple matrix multiplication. So you assume this as a matrix. So sigma tau element. Okay, so let's write this defined as your h sigma tau. Okay, so therefore in the matrix way, so you write it as partial by partial d psi sigma psi tau. Okay, so this is simply rewriting the same kind of equation. Okay, so now our point is, let's assume this equation is correct. Okay, so what it should yield me? Tell me, if this equation is correct, what it should yield me? Tell me. So there are three things we need to consider for a given wave equation or for a relative particle. The first thing is, I should be having, tell me, it should be, first it should be Lorentz invariant, at least. Okay. Second, anybody? Corrective probability density. Interpretation of probability density. And third thing, can anybody just tell me? So if this is a correct, okay, let's say you start with your own wave equation for a relativistic free particle. Clear? What you require it to do? It should be, first it should be invariant under Lorentz transformation, is it?
Yes, sir.
Because when you are talking about the relativistic theories, you need some invariance. Clear? And that invariance is at least it should be Lorentz invariant. Clear? Right hand side should transform in the same way as the left hand side is transforming, or left hand side of the equation should transform in the same way as the right hand side. Clear? Got it? And what it should be? You have seen in Klein-Gordon equation there was the interpretation of probability densities. Clear? You got my point?
Yes,
so you should actually arrive at a definition of a probability density. It should give you the positive probability density. positive probabilities. That means your probability should be restricted between 0 and 1 of figuring out a particle at within given volume. Clear? Got it? And what is the third? It should give you the correct energy momentum relation. Is it? So you should be having a correct energy momentum relation, which in turn should yield you the. Okay, we should actually remove the negative energy solutions. Okay? Is that so? These are the only. These are the main three conditions for a given wave equation to satisfy. Clear? Okay, now let's look at the KG equation first again. KG equation is a second order differential equation. Clear? So that is relatively invariant. That's invariant on Lorentz transform. Can anyone tell me why? Because you are having in KG equation that box operator like this thing. It is equal to 0. Is it?
Yes, sir.
So I should put m square c square by h square. Okay, so this is a invariant quantity. Is it?
Yes, sir.
Okay, so what about this box operator? It's again invariant under Lorentz transform. So that means this equation is invariant under Lorentz transformation. But okay, so it gives you the correct energy momentum relation, but with a negative energy solution. So you are having this problem, and because of the negative energy solution, you get negative probabilities. Clear? Got it? So that is why, as a single particle equation, it does not hold. If you interpret it as a single particle equation. Now we have arrived at another single particle equation. I am assuming this psi is a single particle wave function. Let's say the wave function of an electron that's moving at relative speeds. Clear? Got it? You got my point? Okay. So since it is linear in time derivative here and linear in space derivative here, okay? So that means this side must transform the same way as this side. Or in other words, this minus this equal to 0. So it should be an invariant quantity under Lorentz transformation. Is it?
Yes,
So that means we need to show that whether it is Lorentz invariant or
no.
it is not clear from here. Is it clear? So you don't have clear. I mean, this is not so obvious that this equation is invariant under Lorentz transformation. Why? Because you are having these unknown quantities sitting here. What are these matrices? How they transform under rotational scalar? You don't know. Okay? So, and second thing, okay, so that is what we need to check, whether it is related Lorentz invariant or not. Okay, so usually we call it as a covariance of an equation, whether this is a covariant equation or not. And second thing, what we need to check, does this equation yield me correct probability density? You got it? And third thing, what I need to do, whether, okay, so first whether it gives me the correct energy momentum relation. Okay, let's we can do this in this way. So let's impose this equation yields you the correct energy momentum relation. Okay, and then figure out what are the conditions on these alphas and betas. Okay, what are the conditions they satisfy? Okay, if this has to, if it yields the correct energy momentum relation. Clear? Got it? Okay. So and then we will check whether this the solutions of this equation, when we look for the single particle solution of this equation, whether it yields only the positive energy solutions or both, positive as well as negative. We need to check that. Clear? So we will start from this very point. Okay. So this relation. Okay. So let's check. Energy momentum. So that means, okay. So in this equation, so you are having n components. Clear? Look at the Klein-Gordon equation. There is a similarity kind of thing. In Klein-Gordon equation, this phi is a single component equation. Sorry, wave function. Clear? It does not have any component. How many components you are having here? N components. So that means for each component, it should satisfy the energy momentum relation. Clear? So what is the energy momentum relation in terms of the operators? It's Klein-Gordon equation. You got my point? So what is our energy momentum relation? E square equal to P square C square plus M square C raised to power 4. What is it in the operator for? It's actually the Klein-Gordon equation. So that means each component of this psi must satisfy what? Klein-Gordon equation. Clear? You got it? Okay, so let's try to write it. Okay. So let's proceed. Okay. So let's write it. So we have this Dirac equation for each component, like extra C, let me divide it by I, summation of I, alpha I, partial by partial xi plus beta mc square. So you are having this sigma tau sine tau. Clear? Huh? Beta mc square. Huh? What? What? No, it is here. It was minus I. Huh? I put it as extras by I. Okay. So let's write it then. So it is for a single component. Let me write it for the single component in this way. Huh? So, or I can write like this thing. I will assume this psi to be single component for the time being. Huh? So I will remove these indices. Huh? Clear? So extra C by I, summation over I. It is rewriting the same equation. Huh? So this is for the single component. I am removing this index. So here I am not assuming a column vector. Clear? Got it?
Yes, sir.
Okay. So let's operate then by the same operator. Okay. Operate I cross partial by partial P on both sides. Okay? Clear? So what it is? So it is minus h cross square partial 2 by partial t to psi. That's equal. Now tell me what is this operator corresponding to? So you are having partial like this thing. So it is h cross c by I alpha, summation over I alpha I partial by partial xi psi plus beta mc square psi. So that means this operator is equal to this operator. Summation?
Yes.
The way this operator, so that means they are equivalent operators. Huh? You got my point? Summation? So if I am operating this IH cross partial by partial t on the left hand side, so on the right hand side what I will do? So I will operate this very object. So what is that equal to? So that is simply H cross by I. Let me write partial I like this thing. Partials. So it is an operator beta mc square. Okay, so this operator is acting on this very quantity. Okay, extra c by I. Let me write summation over j because it's a dummy variable. Clear? Okay. So what is that equal to? Multiply. So it is h cross square c square. I into I is minus. Okay. So let me write I summation over j. So it is alpha I alpha j partial to xi partial xj acting on psi. Then tell me what are the other terms. Okay. So let me write here beta mc square. Okay, beta square, beta m square c raised to power 4 acting on psi. Clear? So now let's write the off diagonal terms. H cross. Okay. Now you are having h cross c, then okay mc square. So it is mc cube divided by I. Clear? Okay. So you are having this summation over I alpha I beta partial by partial, another will be beta alpha I partial psi by partial xi. Because, okay, so in this very term, now look here, so you are having beta multiplying this thing. Since alpha and beta are matrices, that is why I have put in the proper order. So beta multiplying these things. This is summation over j, it is the same thing as this. So I have put only the one index. Clear? Got it? Okay. So let's call this as equation first. Now, each component must satisfy what? So you are having, so each component of psi must satisfy kg equation. That is actually the proper energy momentum relation. Okay, so you should not get confused if we are discarding the kg equation, why it should satisfy. So it's because of, I am assuming each component gives you the correct energy momentum relation. In terms of the operators, it is actually the kg equation. Clear? Okay. So what does that mean? So it is, what is the kg equation? So that is right. So in the proper format. So that is minus h cross, okay, partial to psi by partial to 2. So let me put a sigma just to give the, it is for each component. Okay. Okay, so in this case I have not put a sigma. Okay, you can put sigma as well. Okay, but I have not kept a sigma. So it is a single component. Now let's compare first and second. So on the left hand side, you are having the same terms. Clear? Now you are having this as the quadratic term. I mean the second order derivative. So where is the second order derivative? This very object. Okay, so a little bit here we need to symmetrize this. Why? Okay, so you are having xi, xj, it is symmetric in I and j. So that means this product must be symmetric. So this is a matrix multiplication here. Alpha I and alpha j, is it? So it is, these are the product of two matrices. Clear? Now we don't know what this product is, whether this is a symmetric quantity or antisymmetric. I can always put a square matrix in what form? A symmetric plus an antisymmetric part. Okay? So when you put it in that fashion, so you are having a symmetric multiplying it. This is a symmetric part. So that means the antisymmetric part will not contribute. Antisymmetric multiplied the symmetric gives you the 0. This we have studied already. These things you know from your previous courses. So you can write this object as minus h star square c square summation I j alpha j plus alpha j alpha I by 2. Okay, partial 2 psi by partial xi partial xj plus the rest of the terms. So this is the term which I have put here. Clear? Okay, so now let's compare these two. So you are having second derivative here and the second derivative here. Samajh aaye? So what then this should give me? So it means, so comparing the two, alpha I alpha j plus alpha j alpha I. Now look here, you are having minus h star square c square minus h star c square, is it? Only this is the additional term, is it? If I put, let's say it has a delta ij, this very term, delta ij, then sum over j will be replaced by I. What you will get? Partial 2 by partial xi 2. So that's actually Nebula square. Clear? So that is this very term. So it means this should be equal to delta ij. Clear? You got my point? So this combination must be equal to delta ij. And now let's look at this very term. So you are having m square c raised for 4. M square c raised for 4. What is here? So it should give me beta square is equal to identity. Okay? So it should, now look here, if I put beta square as an identity, what do you get? M square c raised for 4. Clear? And what about this thing? So you don't have a linear derivative here. Okay? So you are having a linear derivative in this equation. That means this coefficient must be equal to 0. Clear? Okay? So and you are having this alpha I beta plus beta alpha I, that's equal to 0. So these are the conditions this alpha and beta must satisfy. Clear? So now in order the Dirac equation to, for each component of the Dirac equation to give you the correct energy momentum relation, these equations must satisfy. Clear? Any question or any confusion? Okay, good. Okay, so now let's look at these equations. So what you are having, so you are having alpha I, alpha j plus alpha j, alpha I, that is twice delta I j. Then you are having this alpha I beta equal to minus beta alpha I. Then you are having this beta square, that's equal to identity. Clear? Got it? Now you can check actually alpha I square. So this also gives you, let's put I is equal to j. Clear? So it gives you alpha I square is equal to identity as well. It's an identity matrix. Clear? You got it?
Yes, sir.
Samajh aa? Okay, so now from this let's check the properties of this alpha and beta matrix. Any question? Any question? Okay. So now the first thing is, okay, so let's write. So why these alpha betas we have introduced? H is equal to C alpha dot P plus beta MC square. Is that true? So this is the Dirac Hamiltonian we have. Okay. Now you know if you are having a Hamiltonian, it should be Hermitian. Clear? Because Hamiltonian pertains to the energy. Energy is an observable, and observable quantities we write by Hermitian operators in quantum mechanics. Clear? So now for this object to be Hermitian, since P is a momentum operator, momentum is Hermitian, is it? So that means this alpha and beta must be Hermitian. Okay? So for H to be Hermitian, alpha and beta must be Hermitian. Clear? So what that means? Alpha I dagger, that's equal to alpha I, beta dagger is equal to. Okay? So now let's go to the next property. Okay. So now let's look at that equation. You are having trace of, okay, so you are having this object, alpha I beta is equal to minus beta alpha I. Is it? So it's an anti-commutation. So alpha and beta anti-commute with each other. Clear? Okay. So now let's take a trace. Trace of alpha and beta, that's equal to minus trace of beta alpha I. Okay? So wait a second.
Operate.
So
Alpha.
let's take beta on this side. So let's multiply this by beta on left. So you are having beta alpha I beta equal to beta square alpha I. Okay? So you are multiplying beta on left on this equation. So what this object is? Minus alpha. So now let's take a trace. So you are having trace beta alpha I beta. Okay? So what is that equal to? Minus trace of alpha. Okay? So using the cyclic property of the trace, what you will get? Trace of, so you can take here alpha I beta beta equal to minus trace of alpha I. Okay? So what you get? Beta square is equal to 1. So you get actually equal to trace of alpha I equal to minus trace of alpha I. So which implies that trace of, the only possible solution of this very equation is trace of alpha I has to be equal to 0. So that means your alpha is traceless. Trace means sum of diagonal elements. Now if you are having a matrix, if you can diagonalize that a matrix, so that means sum of eigenvalues is, because all the eigenvalues of a given matrix are on the diagonal of the that matrix. Clear? So you can have sum of the eigenvalues of that matrix equal to 0. Okay. Similarly, you can have trace of beta is equal to 0. How? So you can multiply this by alpha on this side, because alpha square is also identity. Okay, so then we can proceed in the same way. Clear? Got it? So you are having these two things. Okay. So you are okay. So now let's take the another property. So when you are having alpha I square is equal to identity and beta square is equal to identity. Clear? So you are having a square of the matrix is equal to identity. So what does it mean? So what does it mean? What does it mean? Eigenvalues of these matrices has to be plus minus 1. So which implies eigenvalues of alpha I and beta are plus minus 1. Okay? Because only in this case you are having what? Square of these eigenvalues are always identity. Clear? Got it? Okay, so what does it yield mean? Since we started with a wave function that is having n components. Clear? Yeah. Okay, so let's say this is an n component wave function. Okay, so what does it mean? Alpha and beta are n cross n matrices. Now we need to check what is the n. Huh? Wait a second. So let's check n. What is the value of the n? Clear? Okay. Okay. So from this very condition, we are having eigenvalues of a given matrix. They has to be what? Plus minus 1. Okay. And trace has to be equal to 0. So what should be this n? Should this n be odd or even? Even. Okay. So because when you are having an even dimensions, let's take 6 dimensions or 8 dimensions. So you will be having what? What would be the trace? So eigenvalues will be 4 pulses and 4 minus. Okay. And trace will be equal to 0. Only in the even case. If you take the odd case, 1 remains. Okay. So trace will not be equal to 0. So it implies what? So these conditions. Okay, so this condition and this condition gives you n has to be even in nature, even. Huh? So which implies alpha and beta are even dimensions. Now let's check what is the minimum possible dimension you can have. Okay, since we are working in 4-dimensional Minkowski space. Okay, so in 4 dimensions. 4D Minkowski space, okay, alpha and beta are 4-dimensional, minimum possible. Okay, in Minkowski space, okay, let's go to the 2-dimensional is the minimum possible way, is it? Where you can have 1 plus and 1 minus, but that is not possible. You cannot set. Okay, so in 2 dimensions, what are the kind of matrices you are having? Pauli spin matrices. They do not satisfy all these kind of conditions. Okay? Clear? So you are having the basis of the matrices in 2 dimensions is identity. Okay, so you are having the basis of matrices identity, sigma x, sigma y and sigma z. Now you can check with all these matrices, you cannot satisfy these conditions. Clear? Got it? So all these are not. So there is actually a well-known theorem. Usually you have studied in your relativistic quantum mechanics course. So you take it to be 4-dimensional and simply argue these conditions cannot be satisfied. Huh? You cannot satisfy, all these conditions in 2 dimensions. But there is a well-defined theorem, okay, in group theory. So if you have okay. So these alphas, they satisfy a kind of algebra, what we call the Clifford algebra. Okay, Clifford algebra means simply the anti-commutator has to be equal to something. Okay, let's say if you are having some matrices A and B or AI, AJ and so on. If let's say AI, AJ plus AJ, AI is equal to twice the metric tensor, so it is simply a Clifford algebra. Okay, so I will show. Okay, these alpha matrix, we will put it in them in a general format of what we call as a gamma matrices. Okay, so they are more general than these alpha matrices. Clear? Alpha and beta matrices, they satisfy that algebra what we call as a Clifford algebra. Okay, and the minimum possible dimension what we can realize in the Minkowski space is 4. Okay, so there is a well-known theorem. Okay, I can come to that once we will take up the group theory. Okay, I will show you how this dimension, there is actually the relation between the dimensionality of the space-time and the dimensionality of this gamma matrix. Let's say this is the dimensionality of the gamma matrix, and that is equal to 2 raised power n by 2, where n is the dimension of Minkowski space. Okay, so we can prove it. Okay, but in 2 dimensions we can also have. So you can question here: can we have Dirac equation only in 4 dimensions? Because I have written it where you can apply Dirac equation to 2-dimensional systems. Okay, so but there are, you will see there will be only 2 matrices which will give you the kind of this Clifford algebra. Okay, not the all these gamma matrices. Clear? So I will tell you. So you can be having, okay, you can write in principle these Dirac matrices in any arbitrary dimensions, arbitrary even dimensions. Okay, clear? You got my point? Okay. So, but it is actually the choice of the representation what you are doing. Okay. So let's write one of the choices. Okay, so these alpha and beta matrices. So I'll put now them in a general format. Okay. So this alpha I. So this will be only the lecture while we will write these alphas. So we write it as sigma I 0, and beta is equal to identity 0 0 minus I. While sigma i's are Pauli spin matrices. Okay, so let's write now this alpha 1. So that's equal to 0 0 0 1 0 0 1 0 0 1 0 0 1 0 0 0. So that means you have to put sigma x here. Sigma x, sigma 1. So what is sigma 1? 0 1 1 0. Clear? So that's 0 1 1 0 and 0. Rest you put 0. And what is this alpha 2? So that is 0 0 0 0. Then you are having 0 minus I 0, 0 minus I 0 0 0 0 0. Then you are having alpha 3. Okay, so there is an alpha 3. That is 0 0 0 0, then 1 0 0 minus 1, 1 0 0 minus 1, 0 0 0. And what is beta? So beta is 1 0 0 0 0 1. So you put identity minus 1 minus. So this is the one, okay, 4-dimensional representation of these alpha matrices, alpha and beta matrices. Okay, so but there are different ways to write it. Okay, so let me introduce a new notation. Then we will do everything with that. Okay, so we call these alphas and beta as Dirac matrices, but you are having a general way of writing the Dirac matrices. Clear? So let's go to the Dirac equation again. So what you have, okay, so we are having this Dirac equation. Then I will introduce the system of units minus I extra C alpha 1. Yes, any question? Okay, so let me take this thing. Any question? Okay, so now let's multiply this by beta by C on left hand. So like this way. So what you'll get? So tell me. So which yields me I extra beta partial beta by C like this thing is equal to minus I extra, since I am multiplying by beta by C, C will go here. So it is like this thing, beta alpha I. So there is a summation over I, partial by partial xi psi, okay, plus beta by C, beta MC square psi. Okay, what is beta square? That's 1. C and C will cancel. So it will remain only MC. Okay, I have put it in the compactor form. Okay, so now let's define gamma 0 is equal to beta and gamma I that's equal to beta I is 1, 2. Clear? So now what you get? Now tell me. Just tell me. Okay. So beta is what? Gamma 0. What is partial 1 by C partial by partial? Okay, so let's write it. I H trans. So you are having gamma 0. Then you are having partial 0 psi. Clear? Okay. So what then you are having is equal to minus I H trans. Okay, so let me write summation over I. What is beta alpha I? Gamma I. So then you are having partial by partial xi psi plus MC psi. Okay? Okay? Got it? So now let's take this on this side. So what you are having? So IH trans will be common. So gamma 0 partial 0 plus gamma I. So I'll use now the summation convention notation. Okay, gamma I partial I. Okay? So then okay, so you acted this on psi, that's equal to MC psi. Okay? So what you can write it? IH trans gamma mu partial mu. Okay, take that here minus MC psi. That's equal to 0. So this is Dirac equation. Over in the form. Clear? So now I will work with these gamma matrices. Okay? So now let's check what are these. First let's figure out the properties of these gamma matrices. Okay? So let's take gamma 0. Okay? So we have this kind of relation. Okay. So we have this beta is equal to gamma 0. So which implies beta square is equal to gamma 0 square. What is beta square? Identity. So that's equal to 1. So you are having gamma 0 square is equal to identity. Remember it, gamma 0 multiplied by gamma 0. I'll be using this frequently in this course, this gamma 0 square equal to 1. Now let's take gamma I, okay, and also let's take this thing. What is beta dagger? That's equal to beta, which implies gamma 0 dagger is equal to gamma 0. Clear? Got it? Okay. So now let's take gamma, okay, what is alpha? Okay, let's take the dagger of this thing. Okay, so you are having gamma I dagger, that's equal to beta alpha I dagger. So what is that equal to? So that's alpha I dagger, beta dagger. So how much is that? So it is alpha I beta. So what is that? So that's minus beta alpha, because they anti-commute. Clear? So what is beta alpha? It's minus gamma I. So that means, okay, so note these. So these are very important things. Gamma 0 dagger is Hermitian, and gamma I dagger, that is anti-Hermitian. Okay, so remember this. Okay, so now what this will satisfy? I mean, so you are having that relation. So you are having this alpha I, alpha j plus alpha j alpha I, that's equal to twice delta I j. Okay, so now let's put this in terms of the gamma. Okay, so this will be the home assignment for you people. Show that in terms of gamma, this will go as like gamma nu plus gamma nu, it's equal to twice g, sorry, we are using eta mu. Okay, and mu nu are what? 0, 1, 2, 3. Clear? Just show it. So first you will start with I, the element, and then what you will do with the gamma 0. Okay, now let's check it. Let's check whether this is true or not. You do it in the other way around. So what is gamma 0? So let's take 0, gamma 0 plus gamma 0, that's equal to twice eta 0, 0. Is that true? Okay, so how much is that? Gamma 0 square plus gamma 0 square is equal to twice, so that is twice eta 0, 0. What is that equal to? 1. So which implies gamma 0 square is equal to identity, that is beta square is equal to 1. Have you got this first relation? Now let's take the this one. Gamma 0 gamma I plus gamma 0 is equal to twice eta 0 I. Is it? Now since this is diagonal, this means this is equal to 0. Eta 0 I is what? 0. So I is equal 1, 2, 3. So what is gamma 0? So it means gamma 0 gamma I equal to minus gamma I. It is the anti-commutation between what? Alpha and beta, is it? Alpha and beta are what? They anti-commute. What it means now? Gamma 0 and gamma I, they anti-commute with each other. Clear? So what is this? Okay, so let's write it. What is gamma 0? It's beta. What is gamma I? So beta alpha I. What is this thing? Minus beta alpha I. What this is? Beta. So you can cancel beta on both sides, is it? So what remains? Beta alpha is equal to minus alpha beta I. So that means this relation is okay. So you start from this relation. Okay, for let's say I and j, substitute for alpha I and alpha j from that definition. Clear? And you will get actually twice delta ij here. Rather minus you will get, because on this matrix special components are negative. Clear? समझ आवा? Okay, so we call this as the Clifford algebra. Clifford algebra. Okay? So these gamma matrices, so we call them as the Dirac matrices. Clear? Okay, so now can you calculate what is your gamma 0? It is as what beta is. Now what is gamma I? So that means let's calculate gamma 1 first. So it is beta multiplied by alpha 1. So you need to take the multiplication. So now let me put directly. So what is your gamma 0? It is simple as beta. So that's identity 0, 0 minus identity. Clear? Okay. So what is your gamma I? That's simply 0 sigma I minus sigma I 0. So now you will be getting what? A negative sign because of it contains minus 1 here. Got it? So only this is the change. Now this is a representation of the gamma matrices where gamma naught is diagonal. Okay? Is gamma naught diagonal? So we have arrived at a representation of the gamma matrices where gamma naught is. This is one kind of representation. We'll introduce later on another kind of gamma matrices, what we call the chiral gamma matrices. We'll take that to be diagonal. In that diagonal representation, then they are not diagonal. Clear? They are having different values. Clear? Got it? Any question? Any confusion or question? Okay.